So this, okay, thanks. So this is essentially based on the matrix element calculation part of this calculation, which is now integrated in MadEvent, which is, let's say, the outer shell. We get the same cross-section and LHC files as in the Fortran, so this is really functionally giving the same results as the new version of Fortran. On CPUs, we have vectorization, and we reach the maximum SIMD speed up, which is ×8 or ×16 for double and float. However, we have, due to Amdahl's law, there is still a scalar part, and so our overall speed ups are reduced with respect to that. Similarly on GPU, where this is even more striking, because the speed up, let's say with respect to a single CPU core, are much higher, or the order 100 to 1,000. However, the overall speed ups are much lower, because the scalar part is very important there. Although we are also working on the scalar part, we've already improved that. Floats are twice faster than doubles, both for SIMD and for NVIDIA GPUs, for different reasons, and we even added mixed precision modes. We also have an implementation in SQL, where we also have Cocos and Alpaca, but let's say SQL is the most advanced, where we get more or less similar performances, but we also run on AMD and Intel GPUs, and we can, we need to do more detailed performance comparisons for those. And finally, we have future challenges, which include optimizing heterogeneous processing on one GPU and multiple CPU cores and things like this. Now, essentially, where we start from is that we have a program which is MadEvent is the name of the application, which has some parts in Fortran, and also the matrix element calculation, which is the bottleneck in Fortran. From there, since we know that we have to develop this matrix element calculation, we put some, we did everything in CUDA and in C++, and so we built essentially a standalone toy application. In parallel, we also re-engineered the original MadEvent, which the main problem was that it had a single event API, so it was handling one event at a time. And in order to go parallel for vectorization or for GPUs, you need to go to multi-event at a time, so that we could eventually did what we did, which is to inject this new matrix element calculation into it. Now, these are some results, so I will go through them more in detail later, but as I said, you can reach something like ×8 or ×16 for the standalone part, let's say for the matrix element part alone, and then something like ×6 or ×10 for the overall workflow. And for GPU, it's something of the order of higher, more than 100 so in this case, but you are stuck to something like 60 or 100 for the overall part. Now, this was my main messages, and now I'll try to explain how we got there. So I'll give you the long version, which is actually quite long, where I will go through the project evolution, some of the physics, some of the software details. Now let's start. So essentially, I will try to give. I have three parts because I'm trying to give. First, some motivation and implementation, and an outlook, and it fits nicely with giving some time evolution details as well. So first, inception, the motivation, the overview. Why do we want to speed up Monte Carlo generators? Why we chose MadGraph, and why GPUs and vectorization, and why do they work? Then the implementation, so the architecture design, some technical choices, the progress so far. The fact that I didn't say it yet, so I say it now, MadGraph is actually a code generator. So you need to generate the code for every different physics process. Initially, we bootstrapped the project with a very simple lab process, because it was simple and we could hand code a lot of the code. And then we had to integrate this with code generation. Then I'll just give the details for the standalone CUDA and C++, the memory layout, which is very important, especially for vectorization, the GPU kernels. Then details about integration with Fortran MadEvent, some recent performance improvements, and also some words about the abstraction layers. And finally, some outlook, which is mainly the plan to go to a first alpha release, but also things to go beyond. So something about multi-threading, okay, more compilers, I will not cover it, beyond leading order, reweighting, ideas like faster kernels by making them smaller, and things like this. And then even something, what could we do in this area beyond MadGraph and even beyond event generators. So the first part, inception, motivation, overview, how it all started. So I put here some dates. I think this is really something which started, let's say, it was very much triggered by the work we did in the HSF generator working group. So we had this HSF generator workshop at the end of 2018, thanks to Remy, who is here, who pushed for this idea. So there we started reviewing a lot of the computational challenges in event generators. So in 2019, there was, in the context of this, there was a workshop at JLab where the previous work, which had been done on MadGraph on a port GPU, mainly done at Keck, was reviewed. In parallel, we were also doing a lot of work in the working group for the ongoing review of by the LHCC of the HLLHC software and computing. And in the context of this, we did a lot of studies of the computational anatomy, let's say, of generators and ways in which we could improve them. And okay, for instance, there was also a presentation to the LHCC. And in this context, in beginning of 2020, we started this project. So Stefan started, made the first commit to set up the initial executables code and the code repository. And essentially, it was Stefan, Olivier Mattelaro, who is the main maintainer now of MadGraph in Louvain, and myself. And then many people were added, joined the project over time. So I would say that this work, as I said, in the HSF triggered many opportunities because I would say in general, there was a heightened sensitivity to the need to modernize and speed up the HEP software, including generators. There was this breakdown of the computational anatomy of event generators and the way they can be improved, this review of the previous work at Keck. But I think mainly, really, one of the main benefits of this work was that it provided an opportunity for theorists, experimentalists, and software engineers to meet and start collaborating. So people with different backgrounds and with different experiences started working together. And this was in particular the case of Stefan, myself, and Olivier. And I think this was really very nice. Now, a couple of slides on motivation. So why do we want to speed up the event generator? So as you know, the projected needs, especially at the time, so in 2018, but still true, the projected needs for HLHC computing are predicted to outpace the resource growth. And so we need R&D to improve the software and also to use new architectures. And actually, Monte Carlo generators do use some part of that because they use something between 5 and 20% of the compute budgets for Atlas and CMS. And speeding them up may in any case help address this resource gap, but also may help compute more complex processes, which would be useful for the physics at LHC, like multi-jet simulations or even things beyond the next leading order. In the context of the generator working group, we wrote this paper, and I think there's a lot of these issues discussed there, which if you're interested, if you have not seen it already, which probably you have. Now, there's the second motivation, which is related, but not also a bit different, is the fact that GPUs, but also vectorization in CPUs is kind of underexploited in HEP. Now, GPUs especially are extremely important because they provide most of the compute power in recent HPCs. So essentially all modern HPCs, almost all modern HPCs do have a significant fraction of their power coming from GPU. And only a small share of HEP software workloads can run on GPUs today. Well, now today is better than 2 or 3 years ago, but it's still kind of true. Now, also, similarly, most CPUs that we use in WCG have wide vector registers, but only a small share of software workloads efficiently exploit the CPU's vectorization. If you think that you could do in principle up to ×8 or ×16, well, this is not really something that is seen very often. Now, the point is that these architectures, so both GPUs and vector CPUs, they are similar in the sense that they are both best suited to applications which have lockstep processing with limited branching. And this is precisely, as I will try to convince you about, what happens in Monte Carlo generators. So Monte Carlo generators are really ideal candidates to exploit data parallelism in GPUs via SIMT and vector CPUs via SIMD. And I will describe in this talk what we achieved for MadGraph via, for the moment, data parallelism at the event level. Now, what is a Monte Carlo matrix element generator? So essentially, the idea is that it's called Monte Carlo because you throw dices and you randomly generate and process many different events. So these are different phase space points, and this can be parallelized both via SIMT, SIMD, and also multithreading. Essentially, the diagram is like this. So you start by doing you throw random numbers, then you convert those random numbers. You take as input, you convert them to particle momenta. This is the phase space sampling algorithm. Then you take those momenta, you inject them into the matrix element calculation, which gives you the matrix element. And this is really the CPU bottleneck of the current applications. And from there on, you create weighted events, which you can use for doing Monte Carlo integration and compute cross sections, or you can unweight them and produce Monte Carlo samples, which you then pass through Parton showers, hadronization, decay, particle filtering, and detector simulation. So essentially, okay, also keep in mind the physics output of this chain, at least for the generator part, is the cross section and the LHC event file, which is what you pass to the Parton showers. Now, why is this useful for GPUs and vectorization? The point is that this matrix element calculation is essentially one function. So where you have the same function, which is used to compute the matrix element for many different events. So essentially, you are always using exactly the same function, and the only thing that you change is the data that you put as input to this function. And this is precisely what you can do very well on GPUs and also in vectorization. Now, on the left, you see what goes on, let's say, in a modern GPU. Well, this is the NVIDIA Volta white paper. So GPUs are actually a bit simpler because they are able to do things where you have some divergence. So in a way, if you give some data to the GPU where you compute one function and some other data in parallel where you compute a different function, the GPU will kind of nicely follow both branches, both if-then branches, and then it will reconnect at some point and it will continue. However, it is much more efficient, let's say, as you see schematically on this diagram, if you don't have any divergence, because then in that case, every computation is done at the same time, and essentially with one single cycle, you do the computations in parallel. Now, for vectorization on a CPU is exactly the same thing, with the very big difference that on a CPU, either you vectorize or you don't. So it's either the things are really done in parallel because you can do it in parallel with the same function, or otherwise it just doesn't work. I mean, you really have to code it also differently. So in a way, actually coding for vectorization is a bit more complicated than coding for the GPU. But the ideas are the same. If you can do vectorization, you can do GPUs and kind of vice versa. Now, this is the concept of lockstep processing for Monte Carlo generators. Now, you might say, well, Monte Carlo, the name Monte Carlo is actually associated to things like detector simulation, which we know for good reasons is very difficult to parallelize with data parallelism on GPUs on a vector CPU. The point is that the name Monte Carlo is the same because you play the roulette, you throw dice in both cases, but you use these random numbers in two very, very different ways. So on the left, for a Monte Carlo event generator, essentially you do Monte Carlo sampling, which means that the numbers which you throw randomly, they're used to calculate data, which then you pass on to in parallel to this same function. It's what I said, you have the same function on different data, and so the random numbers, they just determine which data you pass to the function. In detector simulation, instead, the problem is that very often this random number determines effectively a different branch or a different decision. So either you do this or you do that, depending on your random number. And this leads to stochastic branching in the code, so a lot of if-then statements. And this is very bad for SIMT and SIMD. So again, okay, then of course, Monte Carlo, there's things like Parton showers, which are a bit in between, as I will say later. But let's say by and large, the point is that for Monte Carlo matrix element event generators, this is really a nice case to do vectorization in GPUs. Now, we are doing this on MadGraph, so MadGraph4 AMC at NLO, which, okay, probably no need to say much about it. You all know what it is. It's one of the workhorses for event generation in Atlas and CMS since many years. From our point of view, okay, I already gave this diagram on the right. Essentially, just to keep in mind two things, that it's got two parts, let's say a software outer shell, which does this random sampling, the unweighting, the I/O and other things, and this is in Fortran. And then you have this inner core, which is the matrix element calculation, which presently it's also in Fortran, but it is the bottleneck. It is the part that we can parallelize, and it is the part that we are going to put on GPUs and on vector CPUs. And MadGraph, okay, it's recently moved from Bazaar to GitHub, so I put down the link onto the GitHub repository there. Now, on top of MadGraph, we started this. Maybe the name is a bit. Somebody told us it's a bit unfortunate. MadGraph4GPU project, because it makes it think like it's MadGraph4, while actually we're using MadGraph5. Well, the 4 here means 4 as in a. We do these 4 GPUs, but okay, fine. MadGraph on GPU project, let's call it. And the point is exactly to speed up the matrix element calculation on GPUs and vector CPUs. We have a code repository with the CI test, issue tracker, development meetings every 2 weeks. As I said, the initial team was Stefan, Olivier, and myself, and then many people have joined that I all thank. The names are given here. Some are active, some have come and already left. Now, one point is, why did we choose MadGraph for our GPU port and not another Monte Carlo generator? Now, I said that we did review at some point the previous work which had been done at Keck for GPUs, but this is not really the reason. I mean, yes, we started discussing that, but none of the work that we are doing today in this project is based on that. I mean, because also, for instance, the matrix element library that was used in this version was different from the one that we have now. Okay, there are some very interesting points in these articles anyway, for instance, the importance of the color matrix. I mean, so it's not that we are ignoring it, but let's say the development itself, the code is essentially rewritten from scratch for GPUs. Now, the main reason why we focused on MadGraph instead is really the fact that luckily Olivier is very actively involved in this project, and he's really the main, well, one of the main maintainers of the upstream MadGraph. And so this is really one of the main reasons also our collaboration is making good progress. I would say in general, somebody had asked me, well, you should point out in this seminar why this I mean, what are the recipes for the success of a project like this? Because it's true that it's very difficult to re-engineer existing software. And I think really you need a good mix of technical expertise, domain-specific knowledge, because neither of them alone would be enough, but also you need really a good collaboration, and the people who know the software must be there and must be actively involved. Now, that said, I mean, we are working on MadGraph, but I want to stress, and I will stress it again, that many of the design ideas we describe are applicable to other generators, because it's really the fact that you have a matrix element event generator that means that you can easily parallelize it for GPUs and CPUs, vector CPUs. Now, just one slide, just to try to guide the next slides, which might be even heavier than before. It's just to say that there are a couple of different branches in my slide. So there's the fact that we started with a simple E plus E minus to E plus E minus process, but then you need code generation. So sometimes I give results for a simple process, but then I talk about event generation. There are actually, let's say, two main branches of development. One which is based on CUDA and C++, and this is the one I will describe. But there is also work which has been done on portability frameworks like Alpaca, Cocos, and SQL, and I will describe this much less in detail. And then there is the fact that I already showed you in a couple of slides that you have a standalone toy application and also this MAD event integrated application. So sometimes I give numbers for one and sometimes I give numbers for the other. Now let's go to the second part. So the implementation, so design technical details and the progress so far. So here, as I said, we started in February 2020. So I'm giving a few dates of our evolution. Let's say what we did until VCHEP 2021, which was June 2021. Essentially, we did add the vectorization, but we were still essentially working with only standalone, so not MAD event integration, and only with the simple E plus E minus process. So at this time, we didn't have yet code generation, and we didn't have the MAD event integration. Then results which were presented last year instead at ICHEP, they do include MAD event, and they do include code generation for more complex processes, and they actually also already include some results from the Cocos and SQL and Alpaca, and these are the two papers which are already published. If you want more details, VCHEP and ICHEP. And then after that, at ACAT, we did, so in October, we presented a few more results, which included already some performance optimization at the level of the overall workflow, so including, let's say, the fact that you have this scalar part and Amdahl's law, and some first numbers for multi-threading and heterogeneous computing. And very important, this is really new since last month, we now have a functionally complete version where we produce LHC files in the same way in Fortran and in CUDA C++. CUDA C++. Now, okay, the point here is that, so this is the main implementation I will describe, and this is using a single source code approach. So essentially, we have a few if-defs to differentiate between the two. I would like to say that the main difference really, but I think this is very general, between a CPU and a GPU implementation is that on the GPU, you access memory on the host and on the device, and on the CPU, it's only on the host. So really, even in the code, most of the difference is about this. Then you have pieces of code which are CUDA specific, so are NVIDIA specific, but this is really minimal. It's like the memory allocation, the kernel execution, and a few specific types, but they're also encapsulated. And all this is encapsulated. This is to say that while we call this CUDA C++, it could be ported relatively easily also to something like HEAP for AMD. I mean, and we plan to do that. Now, the very important part instead is that the rest of the code is at least formally, and I will show you an example, identical for C++ and CUDA. So that's really why we chose to have this approach. Now, we might review this later because there are some slightly unnatural choices, but so far, I mean, it has proved successful, and it allowed us to make rapid progress. Now, an important part for both GPUs and CPUs is the memory layouts. You all heard about arrays of structure of array, arrays of structure of array. Now, in the central part, which is the matrix element calculation, essentially you have input momenta and then output matrix elements. The only part which has a substructure is the momenta. And this is the only part where we tried different AOS, SOA, and AOSOA approaches. In the end, what we're using is an AOSOA approach, because it seems better. But what I want to stress is that for CPU vectorization, AOSOA or SOA is essential. I mean, if you don't have, let's say, the last index in your memory layouts being the one of the things you are parallelizing on, so in our case, the events, you just don't do vectorization. You can't do it. For GPUs, while it's always mentioned that it's often mentioned that you need this. Yes, we tried it. For us, we did keep this because it's faster, but in a way, it's not strictly necessary. It's also because our application at the moment doesn't do very much memory access. Now, if you have an application, this might change in the future because we are going to smaller kernels, so this might change. For the moment, where we have large kernels and few memory accesses, using this array of structural array gives us some improvements. So we do see that they access the memory less, but the overall speed is not much higher. Anyway, since we can do it, we do it. This is just to say again, coding for vectorization is more complex than coding for GPUs. Now, I said that we checked that it is good for GPUs anyway, this array of structural array. Now, it's just here, I just want to mention that you can use this n-site compute tool. There is one specific, two specific metrics that you can collect. One is called sectors and one is called requests. Essentially, you can check how many round trips to the memory you have to do to serve your requests. And we checked that in one case it was n, and in the other case it was 4 times n, which means you have to do much more round trips if you don't use this arrays of structural arrays. And this is called coalesced memory access. So coalesced memory access is good, but for us it's not strictly necessary, but it's clearly good. And since we can do it, we do it. Another heavy slide, but I wanted to give you some formulas because I at least it's, don't have to understand all the details, but just see the one on top left. This is what happens in one event. You have a matrix element calculation is a sum over helicities of something which is a sum over colors of something which is a sum over diagrams. Now, all of these things they need to be done. And for the moment, essentially, we do all of this stuff in a single kernel. So one kernel does one event where we do a sum of helicities, a sum of colors, a sum of diagrams. This might change later, as I will say. It's interesting to know that there are two parts. One part which is the Feynman diagram calculations, and one part which is the sum over colors, which is done with something called the color matrix. And actually, the latter, surprisingly, is becoming the bottleneck as you do more complex calculations. From the point of view of lockstep processing, as I said, all this stuff, so this formula on top left is done for a single event. And the point is that we do that formula for different events in parallel, both on a CPU with SIMD and on a GPU for the moment. Sorry, I went backwards. Now, this is another heavy slide, but I think it's really one of the main points, is the fact that so this is for, it's one example of something which goes on inside the Feynman diagrams, which is called the helicity amplitude calculation. The point here is that we have essentially 3 backends because we have CUDA, we have C++ non-vectorized, and we have C++ vectorized. And what I want to show with this slide is that the code is exactly the same for the 3 backends because we used essentially a type def, which is, okay, his name is a bit stupid, underscore SB means it's something which can be a scalar or can be a vector. The point is that when in that formula you see a plus or a minus, in some cases it's the plus of two scalars on a GPU, in some cases it's a sum of 2 scalars on a GPU, and in some cases it's a sum of 2 vectors on a CPU. And the formula is the same. And this is, let's say, the main thing that we are using, I mean, one of the main tricks that we're using behind the back to do a CPU and GPU at the same time and to do it vectorized. You can see that there is an inline operator because for some of these functions, we do have, we do use things which are already defined. For some things, we have to define our own operators. This is especially because for SIMD, we use something which is called compiler vector extensions, which is extremely useful. However, it doesn't have a complex type. So essentially, the only thing we need to do, the main thing we needed to do was to code a vector complex class for SIMD. Now, these compiler vector extensions, I have another slide which to say why they're very nice. But it's just to say that this design essentially can be done also with something different than compiler vector extensions. For instance, in SQL, it's exactly the same design is being reused to use a vectorized SQL, which uses something which is SQL.vec type. So it's something which does exactly the same thing. So it's a type which contains a vector of things. Now, why did we choose compiler vector extension? I think it's because it's portable, so it's available in GCC, Clang, ICPX. sorry, doesn't require external libraries or tools, but it's also powerful and easy to use. It's powerful because it's as powerful as intrinsics, but it's easy to use and it doesn't need to debug things like auto-vectorization. It's also intuitive because they force you to think in terms of vector types. Okay, I said that there is this minor disadvantage that there are no vector complexes. Okay, and I just want to thank Sebastian Pons because actually all this thing wouldn't have happened without him and his practical vectorization lectures, which is where I found this very nice compiler vector extensions. Now, I said from the beginning that we design for lockstep. Now, can we monitor the lockstep? Can we measure the lockstep? Yes, I think that on GPU, you have something which is, again, I give you a screenshot from this inside computer is one specific metric which you expect to be 100% if you have no divergence. Now, the only problem is that if you have divergence, the number, I don't know how to interpret it. But for us, it's 100%, and so I'm happy. If it is not 100%, it's much more difficult to understand. For CPU, I think that the best lockstep metric is the fact that you get a speed up, which is ×1, ×2, ×4, and ×8, as we do get, as I show here. However, we also do monitor the code, so we disassemble it, and on the bottom left, you can see, I mean, you can categorize the symbols essentially, whether they use XMM, YMM, ZMM registers, and so on, and so you can try to understand how much your code is vectorized. Now, code generation. Okay, this is just to say that it's an iterative development process. We have to start it from somewhere. So we started by generating some code using an existing C++ backend, and then we developed on top of that. We started with this C++ simply because it had little code. We had to generate little code, and then we backported this to code generation. Initially, we were doing this very infrequently. So we had something which we called epochs. Every time we had to restart an epoch, but this was very, very slow because our epochs were like 2 months long. And so developing stuff for GGTT, for instance, wasn't very easy initially. Now we moved to something much better. So this was our early model. We moved to something much better where essentially, this was at the end of 2021, where we go from essentially the moment we put something in C++ and CUDA, immediately we port it to the Python code generator so that then we can generate the same features for a different process, and then we test it on a different process and we iterate. And what, since I will mention a release, something that we still need to do before a release is that we need to integrate the two things, because essentially this code generation infrastructure relies in part on something which is a Python plugin in our own repository, and in part on the upstream framework in the upstream repository. And the two things are a bit, well, it's a bit patched. So we need to integrate this better before we can go to release. Now, why is it important to do this code generation? Well, already because the LHC experiments don't care about lab processes, but also because for us computationally, the simple processes are really not representative of what happens for LHC. The reason is that, for instance, for E+, okay, this is a slide about memory access. If you look at what happens on a GPU with E+, you see that you have a lot of memory access and very little computation, while on the bottom you have GG to TTGG, and there you have much more computation and much less memory access, which is really what we care about and we want to test. I will say many times in this presentation that we are lucky because, okay, for instance, the more complex the process, the less memory access you have. But for instance, the more complex the process, the less relevant is the scalar Fortran overhead. The more complex the process, the fewer events in flight you need to have. So there are a lot of things which really are lucky coincidences. There is one thing which I didn't mention, it's in the backup slides, which is the build time. The more complex the process, the build times can explode. And this is one problem that we will have to fix. Now, I mentioned Amdahl's law. This is Wikipedia. So Amdahl's law is just that if essentially for us, the practical point is this. I said the matrix element calculation is something like 95%, and the rest is only 5%. The problem is that if even only 5%, if the other thing becomes infinitely fast, 5% becomes slow. And essentially, you can, at most, speed up your thing by 20 because your 5% becomes your 100%. And this is this formula here. Now, we do see this this is relevant for us because exactly we do this MAD event integration. And as I said, we have this standalone toy application where we speed up everything, and essentially everything is speed up at the same level. Also the random numbers, also the phase space sampling. While when we go to MAD event, there is one part which we have not sped up yet. And this is here, essentially. So this I showed already in the introduction. It's just to say that essentially this matrix element kernels part, we can parallelize it, but there is this yellow part which remains from the framework before, which remains scalar and becomes the new bottleneck. These are the numbers I showed you before. It's just to say that, okay, does this work here? Oops, I'm trying to, it's this thing here, yeah. Okay, so just to say that, this column is, as I said, is the pure matrix element part and speed up, and this part is the speed up of the overall numbers. But more interesting is actually the times. So these are throughputs, these are events per second, but these are times per event. And here you really understand it. So you have one part, which is this 1.7 seconds, which remains constant, whether you are in Fortran, whether you are in C++, vectorized or not, double or float. And the other part, instead, you see that it goes much lower. And clearly, okay, so here, for instance, it was 5%, and you can go maximum to a factor 20. Now, you do the maths, but you can see that essentially this Amdahl's law is really something that we see. So here for CPU, essentially, I would say we've done all we could do, and what remains to be done is to, if we want to do it even further, is to still optimize the scalar part, which in any case we want to do for the GPU. Now, one detail which is important for some people, if you know this, is just that we have two parts of AVX 512. Now we have one AVX 512 using the 256-bit YMM registers, and one part which is using the 512-bit ZMM registers. This is again an idea from Sebastian, I think, from Sebastian Pons, because he was saying, well, with the ZMM, sometimes you don't get the full speed up. However, with 256-bit registers, it's still better to use this AVX 512 than AVX2, which uses the same registers. And this is true because we use some different instructions. However, initially, so for instance, our VCHEP paper had only these numbers with where this 512Y YMM registers was the fastest. What we did last year was to try some different machines. So for instance, at the Jewels supercomputer, where they have an high-end Intel Gold processor. There they have 2 FMA units. And if you have these machines, we get the full power of a ×8 or ×16. Floating point precision. Okay, I have a lot of material, but okay, I'll try to get at least to the stop first end of this part. Now, floating point precision is important because, as I said, it's important you get a factor 2 by using float rather than double, both in C++ and CUDA for 2 different reasons. For C++, it's because in the same register you fit twice as many floats as doubles. For CUDA, it's typically that on data center CPUs for NVIDIA, you have twice the number of flops in float than in double. Note actually that even in low-end GPUs, you almost have no double precision flops. So this means it would be nice if we could move our calculations to single floating point precision, single precision. However, we cannot do this because it's not enough for physics. There are numerical instabilities, which actually it would be nice to study. If anybody is interested, that would be nice. We did prototype something which we call the mixed precision calculation, where we do some parts of the calculation in double and some parts in float. And I will show an example later for GPUs. But before, I want to show you another thing for GPUs, which is very important, is the fact that when you have a GPU, you also need to fill the GPU, and you have these scalability plots where essentially you have to put a minimum number of threads because you have to keep all the cores busy, all the threads busy. And for us, we see that again, the more complex the process, so let's say at some point with the complexity, which is on a V100, you need at least 16,000 events, while for less complex processes, you need less. Now, even 16,000 is a lot, and we have a few ideas on how to reduce this because this might lead to some problems. I will skip the details because I'm really going too long. I wanted to give you this. Now, this is, I already showed it at the beginning, but here I have a few more details. This is for CUDA, for another process. So again, you have the speed up of the matrix element part and the speed up of the overall thing. Here, I have one part which I didn't have in the C++ slide, which is this last line, which is mixed. So you can see that you have a speed up which is in between the one of double and the one of float, because we are using this float precision for one part and double precision for the other. This is work was done mainly by Zenny and by Olivier. And essentially, it was checked that the physics precision that you get in this color matrix part with floats is enough. And so this is why we believe that we can go to this mixed thing. So it's a way to try to use a bit of float somewhere. Functionality now, very important. Apart from the performance, we also had to, I mean, a lot of the reason why it's taken so long time is that we had to integrate a lot of physics functionality in MadEvent to do this fully functional. So we do this in our so-called Fortran to CUDA C++ bridge. There's things like helicity filtering. There's things like multi-channel, which is essentially the sampling algorithm with MadEvent, running QCD coupling constants, and new. This is the thing which is really from last month, and was our last big missing piece and our last showstopper to release, is this fact that now we get this choice of helicity and color in LHC files done. And this means that we get not only the same cross-section by using Fortran or CUDA C++, but we also get exactly the same LHC file, well, within numerical precision. So this is the road to an alpha release. I would say there is completing the backport of code generation. There's doing a lot of modification to the MadEvent executable. Essentially, the idea is that for those of you familiar with MadGraph, in MadGraph, what you can do is that you, at some point, you do generate this process, launch, MadGraph automagically spawns zillions of processes and then puts them back all together. This thing we don't have yet. Essentially, what we have is that we have a single executable which does what one of those executables does, but we still need to put them all together, all this machinery together, so that the user can just launch, write, launch, and this works out of the box. Also, we need to massage a few things for PP collisions and PDF integration. But stay tuned. We hope that this should come in Q1, Q2. And note this will use a new Fortran version. Now it's 45 minutes, and I have another 50 slides about work in progress and future plans. Now, I don't know if you want me to go through them or not. Stefan says go through them. Okay, I go through them. I'm sorry. For those of you remote, I'm sorry because Stefan is here and I can't see you. So, okay, but I'll try to go quick. So anyway, I have some results about this portability framework. So Alpaca, Cocos, and
Andrea,
yes.
someone is asking on Zoom, can we ask questions? So maybe it would be useful to just pause and ask for questions up to now and then go on.
Yeah, this is what I was thinking. That I mean, but okay, you can ask at the end. But if you have some questions now already, why not? Because exactly the rest is plans. I mean, work in progress. While where we are, well, okay, portability frameworks are more than plans and work in progress. I mean, they are there. But
so
go ahead.
Let's go for other questions.
So this is Eric, and I'm on the phone here. And I have a question on, it's very interesting results. And so it's a question that I'm asking because I'm working with non-scientific clients on AI acceleration, and they are having very good results on CPUs with internal to the CPU accelerators. And when I'm saying good results is that I'm saying like 8 times faster than a machine with GPUs. So I'm wondering, would you be interested in investigating using CPUs that have internal accelerators?
Intel, no.
Because what you're saying, you're doing GPUs, you're doing regular CPUs. I'm saying there is another type of equipment you've not tested.
Yes, I mean, we are in contact with some people who are doing some experimental things which we have not tried yet. But yes, if you have access to some.
So I'm not talking about a research device. I'm talking about stuff that is sold and used by clients on which all the regular AI libraries are available. So I don't know about Fortran compilers. I don't know everything, but in terms of AI math libraries, they are all available for free. You may need to buy a machine to test this, but
listen, thanks for the question. I think the point is that you are saying AI libraries. We are not using any AI libraries, so I'm not sure if the two kind of software developments are similar or compatible. However, it would if you send me a mail about some details about the machine, I think it's something that needs to be followed up offline because.
Yeah, and offline, what I can do, I can organize the call with somebody who knows can explain you the way those CPUs are working.
Maybe actually it's more. I have two of the organizers of this series of talks here. I mean, maybe it's something that could be interesting for this to give a seminar here instead. I mean, not just to me, but why not?
Indeed, this is what I wanted to say as well. That I think for the event generation use case, those devices might not be a perfect fit, but for other use cases, they could be pretty good. Now, for your use case, since you were very clear that memory is not your bottleneck, I don't know how much of an uplift we can hope out of the CPU and GPU devices having access to the same unified memory. Maybe it will give a bit of an uplift.
Mm-hmm. Yeah, just about the memory, I mean, I said it at some point, so I have one slide later on. I mean, it's just that the point is that presently we are doing. So when I had this slide with all the formulas, I said that we are doing all this thing is done in the same kernel. But the point is that if we start splitting all these pieces, all these sums into different kernels, then in that case, a lot of the variables will go to memory, and so to global memory, and we need to organize that. And clearly, the relative importance of memory access to computation will be very different. And so I don't know. I have no idea how it will work. It's something that we have planned. We started to work, but we have no results at all yet. So it's not, I wouldn't say that memory is never important for our use case. At some point, it might become important.
Yeah. Okay.
Okay. So how do I get your email? This is Eric speaking.
Yeah. Okay. Stefan is sending you a message in the chat.
Okay, and let's discuss on the side. I think it's a very interesting subject, and I love what you're doing, guys.
Thanks. Thanks a lot. Very nice feedback.
Any more questions now?
I can wait until the end.
Okay. Thanks, Attila. Okay, so I go back to where I was, which was here. Okay, so we said we have some work with the Alpaca, Cocos, and SQL. There are some differences. Okay, I would say in CUDA CPP, we really designed up front for vectorization, but also for NVIDIA. So for NVIDIA, we have full feature support, and we had the vectorization included immediately. For the scalability, the portability frameworks. We only started. I mean, so this is mainly work by Taylor and Nathan. My understanding is that they only started recently to add it. However, with this SQL vectorization type, which I showed you before, they are getting very nice results. But it's really very recent. We only saw results yesterday, essentially. And so I'm not presenting them here, but I think stay tuned because there might be some interesting results. So there are some differences also. For instance, for us in CUDA CPP, we are not really focusing on multi-threading yet, but we are starting, and I have some slides on this, while in things like Cocos, SQL, or Alpaca, you get this out of the box. Now, what I want to say also is that, so we plan to continue development in parallel using both approaches because, of course, we target a production release at some point, but I think it's also interesting to provide useful feedback about the comparison of the two, which unfortunately I'm not doing now today. So I'm sorry if you were expecting this. I'm only giving a few results. I'm giving a few, however. Okay, this is just a table to say that I would say the main concentrate especially on SQL. I think from me, not because of the intrinsics of SQL versus Cocos versus Alpaca, but at least for the work which has been done so far, which people had the time to do for our use case, the SQL implementation is essentially the most advanced of these three, and it's almost at the same level of CUDA CPP, essentially its functionality. So it's really following very closely. Now, some results here. So here on the left, I have the 4 things for in NVIDIA GPU. So SQL, Cocos, CUDA, and Alpaca, and you see that in this case, they are very similar. Okay, Alpaca was a bit lower, but again, Alpaca is the one which has been maintained, which has been dropped in maintenance earlier. So might be using very, very older code, actually. On the right, instead, you see that one of the nice things about SQL and Cocos, for instance, is that out of the box, you get results for also for Intel GPUs and for AMD GPUs, which in CUDA CPP, of course, we don't yet, even if we plan to do something with heap at some point. Now, you'd see it a bit on this plot on the left, but you see it much better here. One thing that we also discovered recently, but okay, I put it here because we had 2 independent confirmations that it seems to be the case. With our implementation, so again, it might be an implementation feature rather than a feature of the CUDA versus SQL. The CUDA implementation is a bit better for more complex processes, while the SQL one is better for less complex processes. So in a way, CUDA is better because, of course, we care more about more complex processes. But these are interesting recent results which are still being digested, and it will be interesting to understand more in detail what goes on. I think I have one note, yes, which is that, as I said, we also plan to do detailed comparison of multi-threading and vectorization, but it will take time and optimization tweaks. So again, stay tuned, and it is work in progress. Now,
Andrea, sorry, can I just interrupt on the last slide?
Yes, sure.
Just to understand the plots better, is that a linear axis or a logarithmic y-axis?
Very interesting. No, it's this is logarithmic on the y-axis.
So it's actually quite a big gap then.
No, because actually you can't read it. Yeah. It's true. I would have liked to have it also in linear, but we didn't have time to do it in linear. I think that. Oops, sorry. How do I do this? Yes. So here, for instance, this is 6 and this is 4. So it's not. So
okay,
it's not huge.
That'll appear at the slides later.
Yeah, it's not huge. I mean, it's not huge.
Yeah, it's a bit unfortunate that on the top two, you really have no sense of what the scale is.
Yeah, I'm sorry. It's okay. Yeah. Okay. So these are a few more details about working plans, ideas for more speed and features. So something of this started at the end of 2022 because so we had the SEP score benchmarking workshop where a couple of the slides I'm showing essentially come from. We also had the Lugano hackathon, and I should stress again that these GPU hackathons are very, very useful. We did two, one in 2020, one in 2022. They were useful for different reasons, but I think they're very nice events, both for team building in the team, for interacting with experts, and I can only recommend them. Then, okay, as plans, as I said, we hope to have Q1 or Q2 an alpha release, and also very important, Zenny started the PhD work with us, mainly for reweighting and NLO. So the things I'm going to say about reweighting and NLO mainly come from Zenny's work and plans. Now, benchmarking. So you might be familiar with the HEP-Score project. This is essentially the new HEP benchmark that is meant to replace HEP-SPECO 6 for compute resources. It's unlike HEP-SPECO 6, is based on reproducible HEP workloads within Docker containers. The first production version is planned to become production in April 2023 for CPUs only, x86 and ARM. The idea is to benchmark a fully loaded server, so to compare, for instance, is this server better than this other for my workloads? Ideally, also measure how well an application is doing compared to the theoretical power of the server. Now, you fill all the CPU cores by a combination of multi-threading in the application if you have it, and or several identical copies. We included our MadGraph4GPU in a first container of this, and this is very useful for the project because it gives the same physics results on CPU and GPU, which might not be the case for other workloads. Not all the workloads exist on CPU and GPU and give the same results. It also might be interesting to evaluate heterogeneous processing on CPU plus GPU. Now, for us in the MadGraph project, it's also very interesting because it's a way in which I could produce the plots which I'm showing, which are essentially based on several copies of the same application. So how to fill a CPU either with a GPU or without a GPU. These are some numbers. Now, the important thing is that so I had this question from people and from myself, which is, are these benefits that you see from vectorization confirmed? Because all the numbers I gave so far were on a single core. So now here, these are numbers on multiple cores. So the question was, are these benefits of vectorization confirmed when you go to multiple cores? And you see, for instance, here that the difference between this 512Z and the 512Y, which on a single core was 2, is reduced. And this is probably what people are talking about. Now, I should have measured this, but I didn't. Maybe at some point, people are always saying that there is a reduction of the clock when you fully load an AVX 512 server, and this is probably the explanation. So it's like a factor of 2 minus 30%. It's consistent. But okay, it's interesting that you still get a benefit of the full AVX 512 with a full loaded machine. And then, okay, that's also that I tried to give some numbers to show that you are quite nicely exploiting. I mean, you have a factor of 280 with respect to a theoretical maximum of 512, so it's not too bad for the whole thing. Now, this is also an interesting result, which instead is on a GPU. Now, the point here, okay, this is a bit complicated to understand this plot. Now, this is the same kind of plot that I showed before for on the x-axis, you have how much of the GPU you're using, so number of threads essentially on the GPU. However, you have 4 plots, 4 curves, because one is a single CPU, and then one is with 2 CPUs, one is with 4, and one is with 8, copies on the CPU. Now, what you see is that actually the fact that the red curve, which is 8 copies, goes higher is something I don't understand, which is interesting in itself, but I don't understand it, and we will need to understand it. what I really wanted to test, and this proves it, is that by putting more CPU cores, the curves displace themselves to the left. This is very good because it means that you can fill the GPU by using fewer events in each copy on the CPU. And since these events, they have these other implications, like they blow up the RAM of the MAD event, they force imbalanced phase-space processing and so on. This is an interesting thing in itself. And it's also an interesting question for, let's say, a heterogeneous processing, because the fact that, as I said, we have a MAD event scalar overhead, which is becoming the bottleneck. Now, if you can divide that up simply by running more CPU copies of it, then you are speeding it up while getting the same number on the GPU. So it might be some ideas for heterogeneous processing. But again, these are just first results for some ideas. The point here is that I was not sure at all if you could just out of the box share the same GPU through different copies on a CPU, and actually it seems that you can and that you get very good results. There is just a very little overhead doing that.
Before you move on, Andrea, Attila had a question.
Yes, Attila.
Oh, I'm filled with questions. Looking.
Okay, I have time later. So you want to ask it now?
So quickly, then you say number of jobs. Are you really talking about multiprocessing here? Or?
Yeah, I mean, this is, as I said, it's something that I'm doing with this benchmarking infrastructure. So for the moment, the only thing that I'm doing is that I'm running multiple copies, identical copies of the same application. So okay. This is a 4-core CPU, and on a 4-core CPU, I think with hyper-threading, yeah, so with hyper-threading, I'm running 8 identical copies of the same MadGraph4GPU application. Okay.
Then next question: did you use NVIDIA's multiprocessing?
No. I think it's a very good question. I think at some point probably you sent some links somewhere on some forums, and I wrote it down because I found it very interesting. But no, I never had time to try it out.
That could probably even improve these numbers further a bit. But, yeah. But then finally, the big question. So when you modify the number of threads, well, the number of blocks times number of threads, do you always run the exact same calculation? So these are not different calculations, right?
Yes, it's a good question. I mean, the point is that, yes, so it's one of the things I was trying to say before when I said that you get an imbalanced phase-space sampling. I mean, Olivier is very concerned about this because he knows very well the physics. Now, the point is that when you have a complex, I don't know, 4-particle final state, you have many channels of integration because you have many diagrams, and so you have so every channel of integration essentially is a peak in the distributions which correspond for each diagram, and this is the MAD event algorithm. So it's just to say you have, I don't know, you have maybe 1,000 channels that have different peaking structures, and that you have to sample independently. Now, if in each of these channels you start putting minimum 16,000 events, you end up that you have to run millions and millions of events just to get something which is vaguely sensible. And Olivier correctly is concerned that this might, well, already MadGraph was not designed for this, so there are things which might just break. Also, it might take time. Yeah,
I have to admit, some of it I didn't really understand.
But
just to say that, so I am fully on board with you getting a performance uplift from multiple jobs running in parallel, as long as you run with a relatively low number of CPU or GPU threads. Because, yeah, that's exactly what we expect. As long as you're running like thousands of GPU threads, That's nothing for a V100. So yeah, 8 jobs will happily share the same GPU. Well, or at least share it well enough. With NVIDIA multiprocessing, it should be even better. But as long as all the calculations do exactly the same thing in the end, just broken up differently into different number of threads, ideally, I would have expected all of these to converge into a single events per second value towards the high thread count. Because at high GPU thread count, I would have expected the number of CPU threads not to matter anymore.
I'm not sure. Maybe we are saying the same thing. What I would have expected was that this line was flat here. I would have expected that. So here, essentially, the blue one is a single core. So let's say which it reaches the maximum here. I was expecting that the yellow one would reach the maximum here, the green one would reach the maximum here, and the red one would reach the maximum here. So this extra peak, I have no idea where it comes from. While I really like the fact that the peak is reached before, and let's say the idea is also that okay, but this is a detail. I mean, it's at some point, if you have the 8 copies in production might do different things. It's not that they would do the same calculation, but maybe for a different channel. So I mean, they would do something a bit different. I mean, it's not at the warp level, of course. At the warp level, you need to do exactly the same calculation. But
okay, but just because I'm doing something very similar myself as well.
Yeah.
Atlas code, and we are seeing similar results.
Okay, very nice. Then maybe we should
not quite as peaky, but yeah.
Maybe we should discuss it at some point. But again, we have a lot of results. We are trying to first get a release out, and then we have a lot of material for performance improvements. Okay, I continue maybe, because I have a few more things. So as I was saying here, okay, this is what I said before, that we are evaluating lockstep beyond event level parallelism. So the point is that you have this sum here, the sum over helicities. Now the point is that the function inside here is still the same function, just with a different value of the helicity. And we could run that as a kernel for different events, but for many kernels for different helicities, and this might be another way to reduce the number of events in flight, because instead of having 16,000 events in flights, you might have 16,000 helicities in flight. And since each event has maybe, I don't know, say 10 helicities, so it already reduces the number of events by a factor 10. And even more, at some point, that we might even go to individual diagrams in individual kernels, but this is much more, well, futuristic. So I'm not sure when or if we'll get there. But again, it's ideas. NLO, just to say, so we really only have worked on NLO QCD processes. Now, there are some complications with NLO QCD processes. First, they have more Feynman diagrams because, okay, you have one more particle effectively for the same number of external particles, you have one more internal particle. So you have the usual order of magnitude more diagrams, but especially some of these diagrams are loop diagrams. So they have these virtual contributions here with the loop, something like this. Now these are handled by MadGraph with external libraries. And this is the part that we need to understand how to do. Also, you have a matching procedure. So this Monte Carlo NLO, the matching to Parton showers, essentially, which must be applied. But let's say, out of these 3 parts, we think that the Born and real emissions, we should be able to do it as we are doing now for LO, should be exactly the same thing. So we could do it with vectorized C++ and CUDA. The NLO matching, in principle, is handled by MadEvent, and there shouldn't be anything problematic. Now, if I understand correctly, which maybe I don't, the main challenge will be understanding how to understand the computational impact of these loops, because maybe it will become the bottleneck. So I'm not sure. Anyway, we will start to work on this. It's clearly one priority for the next year, and Zeni will mainly work on this. Now, something else Zeni is also working on is reweighting. Now, actually, these are the slides, the plots. They come from another presentation which I gave, which is related to next slide, because I did something related to reweighting, which is on weight derivatives. But Zeni, with Olivier and some others of us, is working here. Zeni already started to work on reweighting with MadGraph. So the idea is to read an LHC file, redo the computation of every event. So reweighting essentially means that you generate a sample with a given value of a parameter. You do the full detector simulation, and then you can reread back that event. You recompute the matrix element for a different value of the physics parameter that you want, and you just reweight each event by the ratio of the matrix elements. Now, since it is a calculation of matrix elements, and this is what we are doing in this new GPU project, you can use that part, and this is what Zeni is already starting to do, and there will be an upcoming poster at CHEP. Now, there are some theoretical and technical challenges, and we are discussing those. So, but it should be something very interesting, and that there's already people in the experiments. So, for instance, Robert, that's working with us, is interested in the applicability of these techniques. Now, the next slide is kind of shameless advertising for something like one of my pet projects, which is weight derivatives, which is very much related to the previous one, because I think that not only weights are important, but weight derivatives are important. But okay, this is a different presentation, but it's just to say that I think weight derivatives can be used to know what is your maximum achievable, what is your best achievable measurement error on any parameter given a luminosity, because it's very easy to take it out. And you can also use it as a second thing to do something like an improved optimal observable method. But okay, there are some pointers there if you're more interested. Don't hesitate to ask me questions. Now, last but one slide, it's about beyond MadGraph. I said that any matrix element of a generator is a perfect fit for vectorization in GPUs because essentially it offers opportunities for 100% lockstep processing at the event level, and even to some extent at the sub-event level. And for instance, it's okay, I think the Sherpa team are already vectorized, are already doing some port to GPU of some parts. There is this blockgen project, but we also did some discussions at one conference about vectorization. So we'll see maybe what will come out of that. There is something completely different that we also started discussing, which is beyond matrix element generators. So clearly, detector simulation is a different beast. There is a lot of stochastic branching, but there is something in between, which is Parton showers, because Parton showers, they have stochastic branching. They actually branching itself of particles, because at some point you decide whether you do a shower or not. However, maybe the calculations before in each Parton shower splitting are exactly the same, and so you could reuse the same idea of data parallelization. And we had some discussions with Phil Hilton and the PCO team on possible collaboration. So who knows? Maybe this is something that it would be interesting to try. Also, just apart from the physics interest or the compute budget interest, but I think really from a HEP software point of view, it's interesting because it's again, it's something which is in between a perfect lost step example and something which is extremely chaotic like detector simulation. My last but one slide is the acknowledgement. So there's, well, first we used a lot of supercomputing centers that we want to thank, mainly so Aurora, Jewels, Marconi, Lumi. Many thanks to our CERN-IT colleagues for providing the help with GPUs. Many people want to mention Sebastian, Adrian, Steve, and Marco for suggestions on vectorization. Igor and Klaus Dieter from Intel for some discussions on vectorization, the GPU hackathon organizers, Domenico and the benchmarking working group, the organizers of the Computer Accelerator Forum, the HSF, the Engineering Working Group, and of course, very important, the original authors of MadGraph. And many thanks from me personally to the MadGraph on GPU team. And I have the same slide we saw. I will not read it again. This was my executive summary. It's now my conclusions. And thanks a lot from me for staying 1 hour and 15 minutes. Those of you who stayed here.
Thank you. Sorry. Thank you very much, Andrea. Excellent. So, any questions, Andrea? Please raise your hand in Zoom or.
Bad sign.
No. Coming. Charles,
this is Eric. I have another question for you.
Eric, you want to jump in? Okay. Yeah, go ahead.
Just and tell me if I'm just getting crazy reading your charts, but have you tried to use FPGAs with tools that convert C++ code to FPGA code?
Interesting question. No, not yet. But I have personally, I have no experience whatsoever with FPGAs. But it's true that since this is such a perfect lockstep processing example, maybe FPGAs would work. I have no idea. No idea.
There are tools that you can actually take a C++ function and export it to the FPGA and then exploit it just like a C++ function, but it runs on the FPGA. And the FPGAs are really faster than the GPUs. Huh? There's no question.
It's a very interesting question. So again, I have no experience with this. Maybe it's just the code is actually quite long, so I don't know if it would fit on an FPGA. But
that's a question. Yeah, I don't have the this is what I'm going to add a paragraph to my email to you about this.
Okay.
Thank you. That's something that people do also. You have very close to you, there is a research center called PSI, and they use this.
Okay.
Because the constraints were that the sensor throughput, this was beyond FPGA dreaming. Okay, it was do it on FPGA kind of.
Okay.
And they do it in production, so it's just not theory. This is practical, done things.
Okay, thanks. I think we can discuss this offline then. Thanks. Okay, Charles, please go ahead.
So one thing that you might be interested in trying is that when you are trying to run a number of kernels concurrently and launch it from a multi-threaded application, as opposed to doing MPS, is to artificially limit the size of your kernels, much smaller than you would normally launch for optimal efficiency if you only had one kernel running on a GPU. If you try to launch multiple threads like that, then you often get a lot of contention with resources on the GPU. And if you try to make each of the kernels smaller, make the launch parameters more restrictive, so the number of blocks, the number of threads per blocks, you can actually get overall, I've discovered at least for certain cases, you can get better overall throughput because you can actually get more kernels running within the confines of the various resources on the GPU. So that might be worth playing with. You see, as you ramp up the number of concurrent threads, if you can actually improve the overall throughput by doing strategies like that.
Thanks, Charles. I think it's an interesting comment. It actually makes me think a bit of some tests that were done in the past with the the maximum register number or things like this. I mean, it's the same idea. I mean, when I said that we wanted to go to smaller kernels, it's exactly our mentors at the hackathon were mentioning always this register pressure and the fact that you have occupancy, and that if you restrict the number of resources, then you can fit more kernels. So I think it goes a bit in the direction of what you're saying. I would say that it's definitely something we need to try, but like this slide is really a very first test. I mean, so we have a lot of interesting work ahead.
Yeah, but maybe just to mention, I mean, you were saying that we were lucky in so many cases, but in this case, we are probably unlucky because we're calculating complex double. So in order to represent one number, we need 4 registers already.
Yeah, no, yes. On the other hand, the numbers that, I mean, like it's a good point, Stefan. We're actually also monitoring register pressure. I didn't say this, but essentially for E mu, we were, I don't know, maybe so out of this maximum 255 registers that you can use on NVIDIA GPUs with like E mu, we were like maybe at 80, and we know that when we go to float, we use like maybe 40 instead of 80. With anything which is GGTT with 2 gluons or more, we are always saturated at 255. So it's there. It doesn't move from there. However, even using the maximum number of registers, we get good results on a GPU. So yeah, we can improve it, but it's not that we are stuck. I mean, something happens and happens fast. Then.
Okay. I see Attila also has his hand on.
Yeah, I wanted to ask a different thing, but just piling on what Charles just said, I just now realized that indeed, since in this plot you only show the total number of threads, so the number of blocks times the number of threads per block, I wonder if that peak structure comes because that's where the sweet spot for threads per block is for this calculation.
It's an interesting. Okay, so I have this. I don't remember how I made this plot. There is this thing which I put here, GT0256. It probably means that. It probably means that they are all fixed at 256 threads per block. I'm quite sure that I fix one number in all the points. It might be 256 threads per block in all the points.
That would make sense, because otherwise it would be a pretty undefined plot. Okay. Yeah. Now, I wanted to open a different can of worms right now.
Go ahead.
That well, with one of my hats on, I was wondering throughout the presentation that unfortunately, running MadGraph, as a user, tends to be a pretty involved process. Even with the current implementation, which only uses a CPU, setting up the correct environment in which you would be able to run the generator, make it generate the code, compile the code correctly, and then run that compiled code. I know that a lot of the questions in Atlas about generators tends to be around this. Now, I was just wondering, since even the current setup is, a bit fragile in how you need to tell MadGraph which compiler it should be using and things like this. Did you guys think already of how all of this information will be passed on to the generation process once you have to choose between different GPU compilers and different backends and whatnot?
Yeah, it goes a bit in this slide. Let's say it's what I was saying, that there is this magic launch command that now essentially. So I have limited. I mean, or maybe Olivier should reply if he's there, but let's say for I have limited experience, but yes, it's true that when you do this launch, magically this starts compilation, it builds things, it even does some code generation, and a lot of things just work kind of out of the box, and we should try to make sure that this works. Now, one of the things I added here is that I said provide and document user hooks for new configurable options, because the fact is that with our environment, this unfortunately for you, Attila, becomes even more complicated, because you are even adding things like, well, do I want to build for AVX 512? Do I want to build for AVX2?
Yes.
This is build option. What is the GPU vector size? Okay, this is more of a runtime option. So we need to even include some of these. Plus, one thing which I actually didn't mention in all the presentation, maybe it's a hidden thing that I hope will not backfire at some point, is the fact that we are using I think we are using fast math, for instance, for all these tests. So even the choice of compile options might not be exactly what is now used in production, and maybe there are some reasons for that. So yes, it's part of this big blob I have in the middle, which is that we have to try to understand how to massage and make consistent the build options. I mean, now how to improve even for the existing Fortran, I don't know, but maybe I mean, if you have some specific feedback, you or the generator group, I mean, you say, you know, by the way, since you're doing this work, why don't you improve this specific point? I mean, I think that if you send it to us, it would be useful.
I would be a bit worried about rocking the boat too much on the existing setup.
Okay.
But yeah, I'm actually just now in a mad dash trying to find all of these options that we have, which is fewer than I thought. I thought we were setting a bunch of environment variables for MadGraph in the Atlas of Line.
Listen, anyway, we are in contact. I mean, I think he even mentioned him on one of the slides. We're in contact with Josh McFadden. That my understanding is that he's the Atlas expert on MadGraph, and we'll certainly interact more with him. Plus, even Walter Hopkins, for instance, he's also Atlas, right? So I mean, we have a number of contacts in Atlas that.
In any case, I'm not super worried. This is just, you know, technical challenge that needs to be solved. And as I said, it's just sort of a can of worms that needs to be handled at one point. But yeah, it can definitely be handled.
Okay, Marcus.
Yeah. Yeah. So I would like to zoom out a little bit, because this whole activity to look at performance enhancements of generators started when we looked a couple of years ago at the projection for high Lumi LHC, where especially the next to leading order fraction of simulation has to be larger, and as a result, it was clear that it becomes a significant amount of the computing. Do you have an estimate when you get the first ideas of whether you actually can make use of GPUs for next to leading order?
Okay, I see your point. So
because this was the main motivation, and the motivation was not to package a MadGraph better that people more easily can run jobs. It was to get ready for high Lumi LHC, and this includes next to leading order.
It's okay. So sorry. So it was not this slide. It's the slides about is really about next to leading order. Now, what I said. So I'll go back to the slide. But I mean, what I said is that in the so in the next to leading order part, there are these the real and the real emissions and the born part, which are essentially they are like what we are doing today. It's just that we never tried it. Voila. But so these diagrams. So there are these three diagrams. So this is the born, this is the real emission, and these two contributions. In principle, we should be able to compute them exactly with what we are doing today. Now, for the central part, which is the loop, is the thing which I have never touched so far. So we discussed it with Olivier, but Olivier didn't seem very concerned that this will be a problem. So I don't have reasons to be concerned. And then the matching is not there. It just that it. I mean, it's the next step of complication, and we haven't done it yet. But again, apart from the loop, which is a bit different, we'll be certainly able to speed up at least some parts of this next leading order. I mean, I'm quite confident this should be possible.
But you have no timeline when you will start trying this?
I don't know if I mean, I think Zenny now is working mainly on reweighting and will present this CHEP poster, but this is actually advancing. And then I'm not sure we started on it's the next thing. So maybe in a couple of months we'll start.
Thanks.
Yeah, I mean, let me just make one comment on it. By the way, I do think it's super important because the work you've done so far in leading order has been a fabulous way of proving that this works, but it's not the bottleneck. Sure. It is the next to leading order that's the bottleneck and the thing which will really hurt us. On the other hand, maybe there's some reason for hope because, you mentioned Amdahl, but there's also Gustafsson who says, do more parallel stuff. And in some respects, that's what you get from NLO. So you actually get more matrix element calculations that you need to do. So perhaps there is some hope that the speed ups can remain very significant for the NLO. But I do agree it's very much a priority to look at.
Is Olivier connected? No. Okay.
Okay, any more questions? I see Charles. Is this an old hand from you? Or you have another question?
Sorry, it's old hand.
Okay. Okay.
So
Marcus.
In my view, it is more important to focus the work on next to leading order than to try to do the parton showers with the GPUs. This is a completely different thing, and it is basically final state calculations. And there are lots of tricks that people can play, but this is core stuff that has to be done. So this is why I'm so keen on it.
Point taken. I think we'll try to make a first release of leading order first, and then see where we are. And
it's not so I'm not criticizing what you have done. I think it's enormous progress from basically not knowing whether this works at all on a GPU to having a good understanding of the performance, having it packaged in a thing that is very close to production release. It's great progress. Just the next step should be the right step.
Okay. Any more questions in the room or on Zoom? Okay, I don't see any. I think we have vastly exhausted our slot.
Thanks a lot again to all of you who are still
everyone.
Here.
Yes.
Thank you very much.
See you in March. Okay. Bye, everyone.
Bye-bye.